Welcome to the 5th Annual Langbein Lecture, which will be presented today by Professor Wilfred Brutzert of Cornell University. This lecture is sponsored by the Hydrology section of the American Geophysical Union, and I'm Mary Anderson, the president of the section. The Langbein Lecture was established to recognize lifetime contributions to the science of hydrology and unselfish service promoting cooperation in hydrologic research. The lecture is also selected on the basis of renown as a lecturer and an educator. Previous recipients include Pete Eagleson, Jim Dube, Nick Metalis, and Shlomo Newman. The lecture is selected by a committee. This year the committee was chaired by Yarada Langwer. Other committee members were David Freiberg and Fred Moltz. The lecture is named in honor of Walter B. Langbein. Like Robert E. Horton, Walter Langbein's contributions to hydrology cross disciplinary boundaries within the field. He is remembered among the world's most versatile, competent, and distinguished hydrologists. Last year, when Steve Burgess introduced this lecture, he showed you a formal portrait of Langbein. I'm going to show you another view of Langbein on an overhead. This is a photo reproduced in the well-known textbook by Dunn and Leopold, and the top schematic shows Hortonian overland flow, and the bottom figure, and I'll read from the caption, shows the feat of Walter B. Langbein exploring Hortonian overland flow. But my main purpose today is to introduce our speaker, Professor Wilf Brutzert. Wilf received an undergraduate degree in agricultural engineering from the University of Ghent in Belgium and graduate degrees from UC Davis. He went to Cornell University as a professor in 1962 and remains there today. Wilf is a member of the National Academy of Engineering, a fellow of AGU, and a recipient of AGU's Horton Award. He is a past president of the hydrology section and remains active in AGU. In fact, he is nominated to run for president of the union in the next election. Like Walter Langbein, Wilf has crossed disciplines within hydrology. As a graduate student, I first became aware of him through his work on the theory of unconfined groundwater flow and estimation of unsaturated permeability. Reading through his publication list of nearly 130 papers, you find that there is a constant reoccurring theme, punctuated by excursions into other diverse areas. These diverse areas include investigations into groundwater recharge, stream hydrographs, unconfined groundwater flow, and hill slope hydrology. But the main theme of his work, and the subject of his lecture today, is his long-standing and continuing work on evaporation. His 1982 book on the subject is a seminal contribution. Among other things, this work led to the ability to predict the fractionation of the different environmental stable isotopes of water, a phenomenon that had been observed by isotope hydrologists but had been unexplained until Wilf published a major breakthrough in evaporation theory in 1965. His recent work on water vapor transport in the atmospheric boundary layer is in the forefront of the current research on regional land-atmosphere interaction. It is my pleasure and privilege to introduce Professor Wilf Brutzert. Well.
Thank you, Mary, for your kind words. 3 years ago, almost to the day, our colleague from Dublin, Professor James Dube, presented what may probably be considered the definitive overview of Walter Langbein's contribution in hydrology. Walter Langbein is the person we honor here today. In the meantime, fortunately, Dube's account has been published in Water Resources Research, and it's now part of the permanent record for posterity. One of the striking features, at least to me, and very obvious in Langbein's work as it gradually evolved from its simple and humble beginnings in civil engineering to full maturity at the USGS, is an increasing and growing concern with the issue of uncertainty and related probabilistic and chance concepts, if you will, in hydrology. This, in his work, is clearly manifested in his contributions on, I just named a few of them, flood frequency distributions, river networks and meandering, and later water resources reliability, and after he retired, even his work on the design of measurement networks. So in trying to decide on a topic for this lecture, I felt that it would be appropriate and a proper tribute to the life and the work of Walter Langbein if I would present here not any deep and profound new concepts, perhaps, but some simple thoughts on the issue of uncertainty in a topic of research with which I'm perhaps a little more familiar, namely the hydrology of land surface atmosphere interactions. Can I have the first slide, please? From bitter practical experience, we all know that the measurement and, as a corollary, the prediction of the turbulent fluxes near the Earth's land surfaces are still subject to large intrinsic error. For example, after Fife, the first Izzle-Skid field experiment, about which I will talk some more later on in this talk, but after Fife, there was no unanimity, but in general, it was concluded by the participants that surface latent and sensible heat fluxes, as measured during that experiment, were generally subject to errors on the order of 10 to 20%. As I said, there was no unanimity, but those were the orders of magnitudes of the errors the authors and the principal investigators felt comfortable with. And those errors of 10 to 20% are equivalent to fluxes on the order of 10 to 40 watts per square meter. These, of course, are not small values. And as you can see at the bottom of the slide, they are almost an order of magnitude larger than the 4 watts per square meter, the radiative forcing, or the greenhouse heat trapping in the atmosphere, which is often quoted as resulting from a doubling of CO2 in present and current analyses of climate change. In other words, current technology is still incapable of measuring those turbulent fluxes with the accuracy necessary to detect climate change signals. The noise is still about 10 times larger than the signals themselves we're trying to detect. The reasons for this uncertainty are twofold. First, the transport mechanisms involve turbulence. And of course, even under the best of circumstances, among the main properties of turbulence are its irregularity and the unpredictability of the details of the flow. Secondly, natural land surfaces are often quite variable, and their characteristics tend to display changes over a wide range of scales. Usually, this variability of land surfaces is so irregular and the details so complicated that, just like the turbulence, it's probably best considered as a random phenomenon. Now, it may very well be that this uncertainty is unavoidable and that there is some kind of uncertainty principle at work here, so that we have, in fact, reached the limits of what can be done in this regard. Still, if such a fundamental principle exists, I think we should try to find what it is and try to determine that uncertainty principle, to determine the bounds on what can and what can ultimately not be known. This slide shows at the top the turbulent flux of any scalar quantity in its raw and its most fundamental form. I'll explain it to you. It is, so you have a flux of a turbulent, of a quantity, an admixture of the air with a concentration C that has an average, as you see on the right-hand side of the top line, an average plus a fluctuation. And the flux itself is then calculated as a covariance. That is a second moment of the fluctuations of the quantity's concentration with the vertical wind velocity. This is all good and well, but this expression is really not terribly useful and fairly useless for most practical problems. So we have to use a different approach in most situations. And for the description of turbulence, at and near the Earth's surface, similarity is probably still the only tool we have available. I can remind you, as I show further down the slide, the schemes, similarity schemes by Prandtl. You may have heard of Monin-Nabokov, Kazansky-Monin, Zilitinkovich, Deerdorf, and many others. But even other schemes, other methods to determine turbulent fluxes, which are not normally associated with similarity, like the Bowen ratio, the surface resistance parameters, which are so popular, and more recently, the various FAT models, soil, vegetation, atmospheric transport models. All these are also grounded, in fact, on similarity. Unfortunately, until now, similarity has been mostly restricted to steady flow over uniform surfaces. And little is known about the boundary layer above randomly variable surfaces with many different and irregular changes in close proximity next to one another. Virtually no attempts have been successful to date to develop any kind of similarity for this type of a boundary layer. The main reason for this inability to develop such similarity schemes is that, of course, the number of variables would become too large to allow implementation of the dimensional analysis, which is the basis for any similarity scheme. Consequently, by the way, I forgot to tell you, at the bottom, you may wonder now, what is a similarity? Well, similarity in simple terms, and all these methods I mentioned a little higher have these features in common. Similarity consists of replacing a second moment for the flux at the top of the slide by a product of first moments, namely a velocity, a mean velocity, times a difference in mean concentration, so the product of two first moments. And then, of course, it's proportional, so you multiply by a mystery coefficient C. And as I said, all these similarity schemes are more or less can be cast in this kind of a form. All right. Similarity, as I just tried to explain, is really the only practical tool we have available. Yet, it has not been extended yet to non-uniform surfaces. So, at the moment, we still have to find the answer to the question on this slide. And I'll read it. To what extent and in what way are similarity formulations and also the corresponding bulk transfer equations and or resistance parameters, etc., originally developed for uniform surfaces, also relevant, meaningful, and applicable over non-uniform surfaces? After all, these similarity schemes are now the bread and butter, the meat and potatoes of most GCM and other modeling exercises. To answer this question, we must consider the structure of the turbulence and also the structure of the variability of the surface. First, the turbulence. We should remember that for our purpose here, the turbulence and the turbulent boundary layer has two important features which we should remember. And these features are shown schematically on this slide. The first one is that the ratio of the characteristic vertical scales and horizontal scales in a boundary layer is normally very small. It's of the order of 1/10 for internal boundary layers, and for internal equilibrium boundary layers of the order of 100. The second feature is that the turbulence itself is highly diffusive and that it has a strong integrating power. To describe or to develop our argument and to focus a little bit, let's first look at a simple scenario of a step change in roughness. Roughness which is uniform here, upwind, and then which suddenly changes to a new roughness. In this situation, the wind is moving from left to right. What happens is an internal boundary layer develops. And this internal boundary layer is what I just mentioned. It has the features. By the way, the vertical scale on this diagram is exaggerated compared to the horizontal scale. But this vertical scale, the height of the internal boundary layer is roughly 10 times smaller than the horizontal scale, typical horizontal scale. In this internal boundary layer, an internal equilibrium boundary layer develops. Inside this internal equilibrium boundary layer, a new equilibrium is developed, and the boundary layer in this region thinks, so to speak, that it has a uniform surface, and that this uniform surface extends all the way to infinity upwind. The second feature of what I just pointed out is also shown here, namely the blurred interface of this internal boundary layer. Let us now take a look at a situation with a number of such simple changes. They're all more or less the same. Each one of them is similar to its neighbors, and they mix the effects of each one of these changes. By the way, these changes could also be disturbances, right? Sources of disturbances at the wall. They could also be sources of water vapor, say the emission of water vapor from a single grass blade or from a single tree. And in this case, in the case of emission of water vapor, you'd have a plume rather than an internal boundary layer. But everything is more or less the same. You have a characteristic vertical and horizontal length scale whose ratio is approximately in the vertical to the horizontal 1/10. Now, if these changes are close enough to each other, the effects of these disturbances tend to blend higher up, and they become indistinguishable from each other. The height above which these effects become undistinguishable is the so-called blending height, and I call it ZB here. Now, so far I've shown you very simple schematic diagrams. Let's now take a look at what we have in nature. And I'll describe to you three large-scale experiments in which I had the good fortune of participating, and we'll see what the measurements above these highly irregular surfaces give us. The first experiment took place in Switzerland in the foothills, in the region roughly between Zurich and Lake Constance. In the distance you see the Alps proper, but the region we're concentrating on here consists of the foothills. Hills very similar to the Adirondacks in upstate New York, hills on the order of 200 to 300 meters and with a roughness height of the order of 3 to 4 meters. So let me quickly go through these. Here is another view of the same region. You see little islands of woods interspersed with villages and farmsteads. Another view on a more foggy day with less visibility. And here are some results of what we measured. This slide, by the way, is taken from a paper that we published, or that I published with a former associate of mine, William Kustas. And this slide shows vertical profiles of mean specific humidity made non-dimensional in some way, and I don't want to go into this. But what we have now is that there are 11 profiles, all measured on different occasions, and they are made non-dimensional. And what I want to point out is that close to the surface, you can distinguish different points. There's a lot of scatter from the measurements on each of these occasions, of these profiles. But higher up, and this is the blending height, at a height of about 200 meters, 150 meters, which is about 50 times the roughness height, you see that they all collapse, these profiles. And you see here that all the profiles show some kind of similarity. Then higher up, at a height of about 300 meters, 200 to 300 meters, which is roughly 150 times to 200 times the roughness height, again, they diverge. And we don't have that similarity anymore. Let's take a look now at another experiment that took place in France, southwestern France, above a forest. I'll give you a few views of how the landscape looked like. It's a fairly flat terrain, sparse forest with an undergrowth of bracken and fern. But this is a mature section of the forest, a less mature section with logging operations going on, a clearing with regrowth, a clearing with agriculture, and then housing developments, little villages. And here, again, several profiles. This comes from a paper that I published with Marc Parlange that shows, again, how many profiles? 8 profiles taken under neutral conditions, this time not of the specific humidity, but of the wind velocity. Again, the profiles are made non-dimensional within a framework of similarity versus the height, again, made non-dimensional. And you see again that roughly at a height, by the way, the roughness of that terrain was around 1 meter, around 50 times 1 meter, so that's around 50 meters, 60 meters. All these profiles collapse onto one, and then again disperse above 150 times to 200 times the height of the roughness and go their own way. By the way, this height, 150 to 200 times the roughness height, is the top of what we consider the surface layer, and I'll come back to that. Another experiment, 5, that took place in Kansas, in the Flint Hills, is characterized by hilly prairie, strongly dissected by riverbeds with trees in the beds. Here you see we look over the prairie and then a riverbed of one creek with the growth of trees. So this is inside one of these riverbeds where we took shelter during hot weather. And this shows a slide on how we determined those profiles, by the way. That was done by radio soundings. Once again, here we go. I show now profiles of potential temperature under non-neutral conditions. This is under unstable conditions. Again, they all collapse on one straight line here between roughly 50 meters and 100 to 100 to 200 meters, all depending on the profile. Now, if we take away, in this case, all the extraneous points that don't belong and that didn't fall within the surface layer, you get something like this, which is almost too good to be true. It's almost like measurements taken in a wind tunnel. Now, these were measurements taken in nature. The same thing with the humidity, the specific humidity, again, made dimensionless in some appropriate way, and versus the height, which is not made dimensionless in this case, but which shows, by the way, the roughness here was also on the order of 1 meter, that we have a collapse of all the curves onto one curve between roughly 50 meters to 150 to 200 meters. So what we have just seen is that each one of these surfaces, which in its own way is quite non-uniform, as you have seen, and quite variable, that each one of these surfaces has indeed a blending height, above which we could detect some kind of similarity. More importantly, the main point here is that from the point of view of turbulent transport, under certain conditions, any surface, no matter how variable it is, can be considered uniform, provided two conditions are satisfied. Namely, that the measurements are made high enough, and secondly, that the surface variability is constant in space. Now, that this surface variability must be constant in space may sound like something of a paradox. After all, here we are. Variability, yet constant. And this, by the way, is part of the oxymoron referred to in the title of this talk. Fortunately, we are not the first to run up against this type of an apparent contradiction. And the issue can be dealt with very conveniently by making use of the theory of the random functions. Now, random functions, as I hate to go over this in an audience with hydrologists, but you all know this, random functions can be characterized by their moments, namely the mean, a number of second moments, and then possibly, though not in standard practice, some higher order moments. Among these second moments, the most commonly used and the standard one is the covariance, also referred to as the autocovariance. A related but less commonly used second moment is the variance, not of the variable, or of the function rather, itself, but of the increments of the random function for different values of the independent variable. In this case, the independent variable being space. This slide shows the definition of this variance for the increments, which is called the structure function or the variogram. And it is defined here for a random function, a homogeneous random function, and that is the point I wanted to come to. A random function is homogeneous if its moments, that is one way to define it, if its moments are independent of space. Now, the definition, as I said at the top of the slide, is for such a statistically homogeneous random function. And what we see is indeed the variance, which is in fact the expected value of the squares. It's the variance of these increments of the function, and this function can be any property, as we will see, surface temperature, surface humidity, what have you, measured a distance h apart. It can be shown that for a statistically homogeneous random function, the structure function, or this variogram, can be expressed in terms of the more commonly used second-order moments. Here, I wrote them down at the bottom of the slide, the autocovariance and the variance itself. And as you can now see with this definition, the variogram should start at 0. For h equal to 0, you have C0 minus C0 equal to 0. It gradually increases to reach a plateau beyond a value of h, beyond which it stays constant. And let's again take a look at some examples. Just to rekindle your memory, let's quickly take another look at 5, at the heterogeneity or the non-homogeneity or the variability rather of that surface. By the way, in the distance you see Manhattan, the city of Kansas State University. Another view, these hills sharply dissected, rolling hilly terrain with grass and then interrupted by small woods. And here again, more of the same. The first slide shows a variogram or a structure function of surface temperature. This surface temperature was measured by means of the TIMS instrument during 5 aboard an aircraft, and it shows that indeed the structure function over 5 for the surface temperature. By the way, this slide comes from a PhD thesis of Russ Qualls. This slide shows how indeed the structure function increases up to a plateau, and where it reaches that plateau we call the lag, or the distance between the points of measurements, the range. And that range is then a characteristic spatial scale of the surface variability. A second slide shows very much the same, but it's sampled over a different area of 5, and it shows that the range, that characteristic spatial scale, is on the order of about 200 meters. A second example, again over 5, was taken from work of Chen and myself, Dao-Yi Chen, and this shows the variogram or the structure function for the NDVI, the normalized difference vegetation index, which is a kind of a non-dimensional greenness index of the surface, measured or determined, rather calculated from green, from some radiances in the visible range of the spectrum from the spot satellite and the Landsat thematic mapper. In this case, the range, I mean the point or the distance where the variogram reaches a plateau, is on the order of 1.5 kilometers. This is just one example for one day. We determined the variogram for many days, and this shows how the range, namely that spatial scale, varies through the season. It starts early on. By the way, day 100 is what we are just about right now. So the prairie is greening up, so to speak, becomes greener and greener, and the spatial scale increases during the summer, then depending on drought or wet periods, and then decreases again in the fall, in periods of dormancy. This slide shows the magnitude of the sill, namely of that plateau. Also shown on the slide is the variance for the entire 5 domain of the NDVI. And what this shows, something that the equation also showed, but that I didn't point out at the time, is that for large values of h, theoretically, in principle at least, the variogram should approach the variance of, or twice the variance rather, depending on what the way you express it, of the entire population. And this shows that indeed over the 5 area we did obtain that. The circles are the plateau of the variogram, the triangles are the variance determined independently of any structure function. And you see that on successive days, they come indeed very close. So what we have seen now is that in the case of a homogeneous random function, the structure function reaches a plateau beyond a certain value of the lag, namely the range. And this fact can be used as a tool to diagnose whether or not a surface is indeed statistically homogeneous. So a random function is homogeneous, or can be called homogeneous, if the structure function reaches a plateau beyond a certain value of the lag, where it becomes equal to the variance, or a multiple, or a fraction thereof. What the slides have also illustrated is that because it reaches this variance beyond a certain range, if one wants to capture the total variability of a surface, one has to sample that surface at least over the distance of the range. So this characteristic scale, the range of the structure function, becomes an important tool also to determine how your sampling should be carried out. This is one important thing to remember here, and which I will come back to. A second important fact to remember is that most natural surfaces, of course, exhibit variability at different scales. I only have to go or explain to you how, if you look at sand grains, as you move from one individual sand grain to the next, you will experience a variability, changes at that scale, moving from one sand grain to the next. Then, as you move up one scale, and you move from one individual grass sod to the next one, again, you experience variability. Then as you go from one plant community, a field of oats, to, say, corn, and then to a little patch of trees, and then to maybe natural prairie, from one plant community to the next, you also experience, again, changes at a different scale. Oh, I forgot to show you these slides. These are just the, by the way, the structure functions for 5 made dimensionless. This is the slide I wanted to come to when I started to talk about scales of the different scales. This shows how the total variability, or the total variogram or structure function of a landscape, can be taken as the sum of individual structure functions. As I said, structure functions for individual grass plants could perhaps be this one here at the bottom. And then the structure function for the change in plant community could be this one. And you can add these structure functions up. The reason for this being that the expected value operator, or the variance operator, is a linear operator, such that the total structure function for the terrain is the sum of the 2 structure functions. All right, I think we can now wrap it up. We have, in this talk, looked at a number of scales, and let me briefly review them. I've talked about the vertical scale, characteristic vertical scales. That could be the height of the internal boundary layer when you have a change in roughness, or the height of a smoke plume released near the ground surface. And then the horizontal scale is the fetch, the distance over which that disturbance has traveled in the atmospheric boundary layer. The vertical scale, there is also a vertical equilibrium scale, namely below which the air has acquired a new equilibrium with the new surface property. The ratio of these scales is 1/10 to 100. I also talked about the blending height. The blending height is roughly 20 to 50 times the roughness length of the surface. I talked about the integral scale, not yet, but it's now perhaps the moment to do so. The integral scale is, under most conditions, equivalent to the measurement height within the air or within the boundary layer. Then I talked about the height of the surface layer, which is on the order of 100 to 150 to 200 times the roughness length, or whichever is larger, 1/10 of the boundary layer. And then finally, we have the thickness of the overall planetary boundary layer. For the surface variability, we have a number of ranges. And those are the characteristic scales for a randomly variable surface. And these ranges are or can be determined from the structure functions that is the variograms. And some of them at different levels of variability, 1, 2, and 3, are nested within each other. Okay, before going on to this third boundary layer, let me quickly review what we have for a uniform, for a homogeneous boundary layer. This is the classical picture with which you're all familiar. Very close to the surface, we have the roughness surface layer, a transition or wake layer, and then the blending height. Above the blending height, we have the law of the wall, the Brownlow layer, or an inner layer, a surface layer. And then above the surface layer, we have an outer region with an inversion layer. This is the idealized picture, the textbook picture, also the picture you see in elementary courses in fluid mechanics. Now, having come up with a number of scales, which I showed on the two previous slides, we are now in a position to set up a few criteria for the applicability. Remember the answer to the question I put on the screen. The applicability of simple similarity schemes that were developed for non-uniform flow. And this slide should help us to determine the robustness of these uniform surface similarity schemes. This slide is a little, it didn't quite come out the way I liked it, but I'll tell you this zone here should be shaded. Also, this zone should be shaded, and with good eyes you should be able to see that. At the origin, we have a transition from a surface with a roughness with a subscript U, denoting upwind. And let's just assume for the argument here, the sake of the argument, that this is a uniform, statistically uniform surface. Then downwind from we have a change in roughness to a, again, statistically homogeneous but variable surface with a level of variability I. So we have a roughness Z0 I. At that level of variability, we have a range derived from the structure function at that level of variability, and then we have a fetch. What is the fetch? The fetch is the distance over which the wind has traveled from, or the air has traveled rather, from the origin to the measuring point. And here it is. This is the measuring point. This zone is the zone within which you can use uniform, or rather similarity schemes developed for uniform surfaces within which you can use them with impunity and within which they are robust. So what conditions do we have to impose on our situation? Well, first of all, that measuring point has to be below the internal equilibrium boundary layer height. And that's what this line says. And that is roughly equal to alpha E, which is 1/100th, times Li, which is the fetch here. So you have to stay below this. You also have to be higher than the blending height for this particular roughness. In addition, you have to ensure that the surface has been sampled adequately. So the air has to have traveled, should have traveled over the surface, over a distance which is in excess of the range for this level of variability. And that's what this dashed line gives you here. Now, we can summarize these conditions in this slide, and I won't do this. This is just a little too Well, we can do that if we had the time, but here they are summarized. The point of measurement, or the internal scale of the turbulence, should be bounded between an upper limit, which is the internal boundary layer, and a lower limit, which is conditioned by the range for that particular surface. If measurements are taken in the mixed layer that is above the surface layer, you use a bulk transfer, the bulk similarity approach, then this would be the condition. Namely that the height of the surface layer is in excess of alpha, again 100th times the range for that level of variability, but lower than the range of our surface. Now let me give you, to make this a little less abstract, let's go through an example to see how practical all this is in real life when you take and make measurements. This shows a kind of a landscape as you might encounter it in an experiment. And let's assume, for the sake of the argument, that we have two levels of variability. So we have two variabilities. We have in between the major roughness obstacles, say, a statistically homogeneous surface consisting, say, of a corn crop, everywhere the same, or lawn, or maybe the prairie terrain we saw in Kansas. So we have a range here in between. Then we have a second level of variability, namely the major roughness obstacles, a little village, these woods, a farm, and so on, that has a level of variability one scale larger than the variability in between these major roughness obstacles. Some people call this micro scale and macro scale. I don't like to do this because micro and macro is really a relative concept. But anyway, now let's assume that we have a mast here at M, and we're going to measure fluxes and apply some kind of we want to apply some kind of similarity scheme. What I will now do is try to explain how we encounter different regions and how within those different regions various similarity schemes are applicable. As we start at the surface, the lowest measurements will take place within the grass, within the corn. This is canopy flow. Highly irregular, highly disturbed. Forget it. We don't have any good theory available to use those measurements within a simple similarity scheme. Above the blending height for this level of variability, we come within this first internal equilibrium layer, the same internal equilibrium layer that develops behind these major obstacles after or behind this change in roughness. Here we can measure and we can apply any one of those similarity schemes. And what we will be measuring with the turbulence in here is the flux from this surface. As we move higher along our mast, we'll again be measuring stuff. We'll again be out of luck. This is a highly disturbed region. It's the outer region of the internal boundary layer, again, for which we don't have any good theory. Some studies have been made on this, but they all have been ad hoc for special situations, and there is no general similarity available. So we're out of luck. If we have measurements here, it's really very difficult to determine what they mean and how they can be related to the surface flux. They can be Bowen ratio measurements. They can be measurements to be used in a model, the SFAT model, what have you. But as I say, you're really on your own, and we don't have good theory to relate whatever we measure in here to the fluxes, turbulent fluxes. We move higher up, we're still within a disturbed region, And once we pass the blending height for the second level variability, we're again in an equilibrium layer. In this equilibrium layer, however, what we're measuring now is the effect or the multiple effect of all these roughnesses, including the effects from the small roughnesses, all blended and mixed together above this blending height. At this level, or above this level, we have what is commonly referred to as a regional surface layer. And the regional surface layer is, in fact, what I have shown in the case of those three examples, Switzerland, southern France, and in Kansas. And from these measurements, as you saw in the dimensionless representation, you can relate the measurements, the mean measurements, to surface fluxes. All right, this leads us to a few simple conclusions. And these are that many highly variable surfaces, which many people call heterogeneous or non-uniform. And by the way, I'd like to make a plea that we clean up, I'm not a linguist, but we should clean up our language and somehow agree among ourselves what heterogeneous, what homogeneous, statistically homogeneous means, what variable means. See, in antiquity, all these words come from ancient Greek and Latin. All these words mean, in fact, the same thing. Homogeneous, uniform, right? Stationary, spatially stationary. It's very difficult on the basis of the etymology to decide what the difference is. So we have to somehow come to an agreement. Anyway, many of these surfaces can be considered homogeneous, albeit statistically homogeneous. And an important factor in the assessment of homogeneity is the reference height at which we measure, at which we take our measurements. And then finally, what I like to do is make a plug for the measurement or the use of remote sensing technology, and that it is probably the only technology we have available at present to carry out structural analysis for highly complicated surfaces. Thank you very much.
Please join me in thanking Professor Brutzert for an excellent lecture. I'm sure Wilf will be available if anyone wants to speak with him for a few minutes after the lecture. Those of you who are attending the hydrology section lunch, that room number is 337, and the luncheon begins promptly at noon, and we'll have a short business meeting about 12:30 or so. Thank you for coming.
Oh, yes.